James Webb just sent back new images of Pluto, and scientists are analyzing them right now. What they found confirms a decade-old theory nobody could test, until today. For most of human history, Pluto was nothing more than a dot, a faint, flickering smudge of light captured on a photographic plate in 1930, so distant and so dim that even the most powerful telescopes on Earth could barely resolve it into anything more than a single pixel. For decades, that's all Pluto was to us, a point of light. A mystery hovering at the edge of the solar system, 3 billion miles from the sun, so cold and so far away that many scientists simply assumed there was nothing interesting happening there at all. A frozen rock, a dead world, the kind of place you study once, catalog, and move on from. That assumption held for almost 85 years. And then, in the summer of 2015, everything changed. NASA's New Horizons spacecraft, after a 9-year, 3 billion mile journey through the solar system, screamed past Pluto at over 30,000 miles an hour. And for the first time in human history, we saw Pluto's face. What we found broke every expectation scientists had walked in with. Instead of a dead, cratered ball of ice, New Horizons revealed a world of towering ice mountains, some as tall as the Rockies. Vast plains of frozen nitrogen so smooth and so young-looking that they couldn't have been more than 10 million years old, which in geological terms is almost brand new. A heart-shaped region so striking it was visible for millions of miles away, later named Tombaugh Regio after Pluto's discoverer. And alongside all of that, something nobody was fully prepared for. A thin, hazy atmosphere wrapped around the planet, and inside that atmosphere, layer upon layer of pale blue haze, stacked on top of each other like sheets of gauze, stretching more than 180 miles above the surface. That haze should not have existed, or at least not the way it did. Here's the problem scientists ran into almost immediately. Pluto is small. It's about 2/3 the size of our own moon. Its gravity is weak, its atmosphere is thin, barely a whisper of nitrogen, and methane gas escaping into space every single day. And Pluto is far. It receives about 1,000 times less sunlight than Earth does. At that distance, with that little energy reaching the surface, nobody expected Pluto to have anything resembling weather or climate or the kind of complex atmospheric structure you'd see on a planet like Earth or Mars. And yet, there it was in the New Horizons images. Layer after layer of blue haze, visible in dramatic backlit photographs as the spacecraft looked back at Pluto with the sun behind it, silhouetting the tiny world against the blackness of space. Scientists had a haze they couldn't fully explain, sitting on top of an atmosphere behaving in ways nobody had modeled. And for almost a decade, that mystery just sat there, unresolved, waiting for technology powerful enough to actually study it properly. That's where our story really begins. Not in 2015 and not today, but in 2017, 2 years after the New Horizons flyby, when a young planetary scientist named Si Zhang, working at the University of California, Santa Cruz, sat down with his research team and asked a very simple, very dangerous question. What if the haze isn't just decoration? What if the haze is actually running the show? It's easy to underestimate how bold that idea was at the time. For decades, when scientists modeled the atmospheres of distant, icy worlds, they focused almost entirely on gases: nitrogen, methane, carbon monoxide, the invisible molecules that made up the bulk of the atmosphere. Haze, when it was considered at all, was treated as a side effect, a cosmetic feature, something that happened because of the atmosphere, not something that shaped it. Zhang and his colleagues proposed something radically different. They suggested that Pluto's haze wasn't a passive bystander in its climate. They suggested it was an active participant, possibly even the single most important factor driving how heat moved through Pluto's atmosphere. Here's the actual mechanism they proposed, and it's worth slowing down for because it's genuinely elegant. Pluto's atmosphere is mostly nitrogen, with a small but crucial amount of methane mixed in. When sunlight, even the weak, distant sunlight that reaches Pluto, hits that methane, it triggers a chain of chemical reactions. Ultraviolet photons break apart methane molecules, and the fragments recombine into more complex hydrocarbons. Then even more complex organic molecules called tholins. These aren't simple molecules. They're intricate, carbon-rich compounds, similar in some ways to the reddish-brown organic haze particles found in the atmospheres of Saturn's moon Titan. As these tholin particles form high in Pluto's atmosphere, they slowly drift downward under the influence of gravity, falling toward the surface over the course of weeks and months, and as they fall, they interact with sunlight in a very particular way. During Pluto's long day, these haze particles absorb incoming sunlight, even the faint sunlight available at that distance. Then, during Pluto's long, cold night, they release that stored energy back out, not as visible light, but as infrared radiation, essentially heat, radiating outward into space. Zhang's team proposed that this cycle, absorbed from sunlight, radiated away as infrared, happening across trillions of tiny haze particles throughout Pluto's atmosphere, was actually more efficient at controlling temperature than the gas molecules themselves. In other words, The haze wasn't just floating there, looking pretty in New Horizons backlit photographs. The haze was potentially acting like a planetary scale thermostat, cooling Pluto's upper atmosphere far more effectively than anyone had assumed possible. And this theory made a very specific, very testable prediction. If the haze really was doing this much thermal work, then Pluto's atmosphere should be dramatically colder than standard models predicted. Not colder by a degree or two, colder by a wide, glaring margin. Zhang's team calculated that if their haze cooling theory was correct, Pluto's upper atmosphere should sit at somewhere around negative 333 degrees Fahrenheit. That's about 203 degrees below zero on the Celsius scale. For context, that's roughly 30 degrees colder than what conventional atmospheric models, the ones that only accounted for gas molecules and ignored the haze's role, were predicting. 30 degrees might not sound dramatic if you're talking about the weather outside your window. But in planetary atmospheric science, a 30-degree discrepancy is enormous. It's the difference between a theory being roughly right and a theory being fundamentally incomplete. If Zhang was correct, it meant that haze-driven cooling was an entirely new kind of climate mechanism, one that hadn't been properly accounted for in how we understood not just Pluto, but potentially other hazy worlds throughout the solar system and beyond. There was just one enormous problem. In 2017, there was no instrument on Earth or in space capable of actually testing this prediction with any real precision, measuring the precise temperature of an atmosphere that thin, that cold, and that far away, while also isolating the specific infrared signature of haze particles as opposed to gas molecules, required an instrument with a level of sensitivity that simply did not exist yet. Zhang's theory sat there, published, respected, debated in academic circles, but fundamentally untestable. A prediction frozen in place, waiting for the right tool to come along. That right tool arrived in December 2021, when the James Webb Space Telescope launched from French Guiana, folded up like origami inside an Ariane 5 rocket, destined for a gravitationally stable point nearly 1 million miles from Earth called the second Lagrange point. Webb wasn't built specifically to study Pluto. Its primary missions involved peering back toward the very first galaxies formed, after the Big Bang, studying the atmospheres of exoplanets orbiting distant stars, and unraveling the earliest chapters of cosmic history. But Webb's infrared instruments, engineered with a level of sensitivity that dwarfed anything that came before it, happened to be exactly what was needed to finally test a 5-year-old prediction about a tiny, frozen world at the edge of our own solar system. By 2022, once Webb's mirrors were aligned and its instruments calibrated, astronomers pointed it toward Pluto. And this wasn't a simple task. Pluto and its largest moon, Charon, are so close together and so far from Earth that from our vantage point, they can appear to blur into a single object in less sensitive telescopes. Webb's infrared instruments, though, were finally sharp enough to cleanly separate the infrared signals coming from Pluto and Charon individually, something that had been a persistent challenge for ground-based observatories for years. And once that separation was achieved, once astronomers had a clean, isolated infrared signal specifically from Pluto's atmosphere, they finally had what they needed to test Zhang's 2017 prediction directly. The results came back, and they matched. Not approximately, not in the general ballpark. They matched the predicted signature of haze-driven cooling with remarkable precision. The faint infrared glow that Webb detected coming from Pluto's atmosphere lined up with what Zhang's team had calculated 5 years earlier, based purely on theoretical modeling of how Tholen haze particles should behave. Zhang, reflecting on the moment, said something that captures just how unusual this kind of scientific validation really is. In planetary science, it is not common to have a hypothesis confirmed so quickly within just a few years of it being proposed. Most theories in this field take decades to test, if they're ever tested at all, given how rare and expensive missions to the outer solar system are. Zhang said the team felt lucky and genuinely excited because moments like this, a clean, direct confirmation of a specific numerical prediction, are vanishingly rare in a field where most of your subjects are hundreds of millions or billions of miles away. So what does this actually mean? Let's break down what scientists now understand about Pluto's atmosphere now that Webb has confirmed the haze cooling theory. Pluto's atmosphere behaves unlike anything else observed in the solar system. It's not primarily the gas molecules, the nitrogen and methane themselves, that are dictating the temperature of the upper atmosphere. It's the haze, those tiny, complex organic particles, formed from sunlight breaking apart methane and reforming it into heavier compounds, are absorbing solar energy during Pluto's long day and radiating it back out as infrared heat during Pluto's long night, more efficiently and more significantly than the surrounding gas ever could. This makes Pluto's atmosphere behave like what scientists are now calling a new kind of climate system, not gas. Dominated, like Earth's atmosphere, where water vapor, carbon dioxide, and other gases are the primary regulators of temperature. Haze dominated, a climate system essentially run by solid particles suspended in the air, functioning almost like billions of microscopic radiators, constantly cycling energy in and out of the atmosphere. This is where the story gets bigger than just Pluto. Because a haze-dominated climate system isn't just an interesting quirk unique to one small, frozen world at the edge of our solar system. It potentially reshapes how scientists think about atmospheres throughout the cosmos, particularly on other hazy bodies. Saturn's moon Titan, for example, has long been known to have a thick, complex, hazy atmosphere, and scientists have wondered for years whether similar particle-driven thermal processes might be happening there too, just on a larger scale. Neptune's moon Triton, an icy world with surprising similarities to Pluto, may share this mechanism. And beyond our own solar system, astronomers using Webb to study the atmospheres of distant exoplanets have increasingly found evidence of hazes and clouds playing significant, sometimes dominant roles in shaping those atmospheres too. If haze-driven cooling turns out to be a common mechanism rather than a Pluto-specific oddity, it could mean that a whole category of climate physics has been underweighted in how we model atmospheres across many different kinds of worlds, from icy dwarf planets in our own backyard to gas giant exoplanets hundreds of light years away. There's also a more personal, more Earth-centered angle to this discovery. And it's one of the reasons scientists have described this finding as offering clues to our planet's ancient atmosphere. Early Earth, billions of years ago, before the rise of oxygen-producing life, may have had an atmosphere chemically similar in some ways to Pluto's today, rich in nitrogen, containing methane, and potentially wrapped in a comparable organic haze produced by similar photochemical reactions, triggered by sunlight breaking apart methane molecules. Some researchers have long speculated that a haze layer on early Earth could have played a significant role in regulating the planet's temperature during a critical period before life as we know it took hold, possibly even protecting fragile early organic molecules from harmful ultraviolet radiation while simultaneously influencing the greenhouse effect and overall climate stability. Testing haze-driven cooling mechanisms on a present-day world like Pluto, where we can directly observe and measure the process happening in real time, gives scientists a working laboratory of sorts, a living example of haze physics in action that they can use to refine their models of what Earth's atmosphere might have looked like and behaved like billions of years before humans existed to observe it. Let's also talk about what this means for how we picture Pluto itself, because the picture has shifted dramatically over just the past decade. When New Horizons flew by in 2015, it already shattered the old image of Pluto as a dead, static world. What Webb has now added is a second layer to that story. Not only is Pluto geologically active, with young ice plains and evidence of ongoing surface changes, its atmosphere is dynamically active too, governed by an intricate, self-sustaining thermal cycle involving billions of microscopic haze particles constantly absorbing and radiating energy. Pluto has gone, in the span of about a decade, from being dismissed as an inert, frozen leftover at the edge of the solar system, to being recognized as one of the most atmospherically fascinating and unexpectedly complex bodies we've ever studied. And there's still more to learn. This confirmation of the haze cooling theory isn't the end of the story. It's really more like the opening chapter of a much longer investigation. Scientists are now using this confirmed mechanism as a foundation to ask deeper questions. How does this haze-driven cooling process change across Pluto's extremely long seasons, given that a single Pluto year lasts about 248 Earth years, meaning the seasonal cycles we're only beginning to observe now unfold over multiple human lifetimes? Does the thickness or composition of the haze layer shift as Pluto moves along its elongated orbit, sometimes closer to the Sun and sometimes much farther away, given that its orbit is more eccentric than any other major body in the solar system? Could this same haze-driven cooling process be actively happening on other similarly hazy small bodies scattered throughout the distant, largely unexplored region known as the Kuiper Belt, the vast ring of icy objects beyond Neptune's orbit that Pluto itself is a part of? Follow-up observations using Webb are already being planned and, according to researchers, conducted specifically designed to track how Pluto's atmosphere changes over time, watching for seasonal variation, monitoring for any shifts in haze density or altitude, and continuing to refine our understanding of the surprisingly complex thermal relationship between Pluto's surface, its thin atmosphere, and the haze layers that appear to be quietly running the whole system. It's worth pausing here to really sit with how significant this moment is, scientifically speaking. This isn't a story about a single dramatic new photograph capturing public imagination for a news cycle and then fading away. This is a story about the scientific method working exactly as it's supposed to, just playing out on a timescale most of us rarely get to witness. A researcher proposes a bold, somewhat unconventional theory in 2017. That theory makes a specific, falsifiable numerical prediction. Rather than that prediction sitting untested for decades, waiting for the next multi-billion-dollar mission to a distant world, or worse, never being tested at all, A new tool arrives, just a few years later, with exactly the right capabilities to check the math, and the math holds up. That kind of clean, relatively rapid confirmation is genuinely rare in planetary science, where most of our subjects sit hundreds of millions or billions of miles away, and where testing any given hypothesis often requires waiting for a specific, expensive, meticulously planned spacecraft mission that might not launch for another decade or two. There's also something worth appreciating about the broader arc of Pluto's story within the history of astronomy itself. Discovered in 1930 by Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona, Pluto was initially celebrated as the 9th planet in our solar system, a triumphant discovery that captured global attention. For decades, it held that status, taught in classrooms, memorized by generations of schoolchildren as the final planet before the edge of the solar system. Then, in 2006, following a contentious and widely publicized debate among astronomers over how to properly define what a planet actually is, the International Astronomical Union formally reclassified Pluto as a dwarf planet. It was a decision that remains debated and, for many, emotionally charged, even today, nearly 2 decades later. But here's the thing about that reclassification that often gets lost in the discourse. Whether or not Pluto carries the label planet or dwarf planet, that classification debate has essentially nothing to do with how scientifically fascinating the object itself actually is. Pluto doesn't care what we call it. It has continued, quietly and consistently, to surprise us at every single stage of serious investigation. The Hubble Space Telescope, in the years before New Horizons, gave us our first blurry hints of variation across its surface. New Horizons in 2015 revealed staggering geological complexity that upended decades of assumptions. And now James Webb has confirmed that Pluto's atmosphere operates according to a genuinely novel climate mechanism, one that may have relevance far beyond this one small, distant world, potentially reshaping how we understand atmospheres across our solar system and beyond. So where does that leave us? James Webb didn't break the laws of physics when it looked at Pluto, and it didn't stumble onto some inexplicable anomaly that defies scientific understanding. What actually happened is arguably more impressive than that. Webb confirmed physics working in a way scientists had carefully, rigorously predicted years earlier, but had lacked the technological capability to actually verify. That distinction matters. It's the difference between mystery for the sake of spectacle and genuine scientific progress, built patiently, one confirmed prediction at a time, across nearly a decade of careful theoretical work followed by precise observational validation. Pluto, this tiny frozen world at the very edge of our solar system, 3 billion miles from the Sun, orbited by 5 known moons, discovered by a young astronomer in Arizona in 1930, demoted from full planetary status in a controversial 2006 vote, and then gloriously revealed in unprecedented detail by a spacecraft flyby in 2015, has once again reminded us of something. Distance and darkness and cold do not mean simplicity. Even out there, nearly 40 times farther from the Sun than Earth is, where sunlight arrives 1,000 times weaker than it does here, where temperatures plunge to nearly 400 degrees below 0 Fahrenheit, there is an intricate, active, dynamic climate system quietly operating. Billions of microscopic haze particles, born from sunlight splitting apart methane molecules, drifting slowly downward through a thin nitrogen atmosphere, absorbing energy by day and releasing it by night, functioning as an elegant, self-sustaining planetary thermostat that nobody fully understood until a scientist made a bold prediction in 2017, and a telescope built to study the edges of the observable universe happened to confirm it, almost as an afterthought, nearly a decade later. That's the real story behind the headline. Not laws of physics breaking, but laws of physics being understood a little more deeply than they were before. And somewhere out there, in the cold and the dark, at the very edge of what we've been able to explore, Pluto is still waiting, still full of details we haven't uncovered yet, still capable of surprising the people who study it, one careful observation at a time.